Good morning children, welcome to GCC Education online class. So last previous session la vandu namba Gauss law introduction paathom. In the session la vandu we are going to see applications of Gauss law. So applications la vandu we have 4 different applications. So application paakradhukku munadi இந்த Gauss law namba derive panna equation vandu first namba recollect pannikalam. The total electric flux phi E is equal to closed integral E vector dot dA vector is equal to Q enclosed by epsilon naught. So in the expression தான் நம்ம ஃபைனலாக derive பண்ணோம் last sessionல. So இந்த expression யூஸ் பண்ணி தான் நம்ம we are going to find the electric field due to an infinitely long charged wire. So the first application is very very important 5 mark question. So இன்னைக்கு இருக்கிற இந்த 4 applications it's more important in the examination point of view. அதனால நீங்க நல்லா தரவா படிச்சுக்கிறது நல்லது. So electric field due to an infinitely long charged wire அதனுடைய electric field கண்டுபிடிக்கிறதுக்கு so first let us take infinitely charged wire எடுத்துக்க முடியாது. We will take a charged wire of length L. Like wire வந்து இந்த மாதிரி மெலிசா இருக்கும், infinitely long charged wire, and it let us assume it has got positive charges stored in it. So the total charge that is enclosed in this length L, we are taking only for convenient for derivation, we are taking the length as L. So in this whole length L of the charged wire, we have the total charge enclosed Q enclosed. So total charge enclosed in this length L is equal to Q enclosed. So L length la irukra charge Q enclosed na unit length ku evlo charge irukum அப்படின்றது ஈஸியா நம்ம எழுதலாம் mathematically. Charge per unit length which is lambda, this we have already learnt in the beginning part of the lesson. Linear charge density lambda, surface charge density sigma, and volume charge density rho, இதெல்லாம் வந்து நம்ம ஏற்கனவே பார்த்தோம் in the previous portion of the lesson. So அதே தான் திரும்ப இங்க நம்ம யூஸ் பண்றோம். Charge per unit length which is the linear charge density denoted by the letter lambda is the total charge divided by the length L. So இதில இருந்து we can find Q enclosed which is nothing but division la irukka lambda வந்து you can bring it to this side. Q enclosed is equal to lambda L. இந்த Q enclosed தான் நம்ம இங்க சப்ஸ்டிட்யூட் பண்ண போறோம் இந்த எக்ஸ்பிரஷன்ல. So இந்த derivation பார்ட்டுக்கு போறதுக்கு முன்னாடி we all know Gauss law apply பண்ணனும்னா first Gaussian surface வந்து first நம்ம assume பண்ணனும். So Gaussian surfaceக்கு வந்து symmetry கண்டுபிடிக்கணும். இந்த symmetry கண்டுபிடிக்கிறதுக்கு in this wire let us take from midpoint ல இருந்து ஒரு r distance ல let us take a point P. So இதுக்கு முன்னாடி let us just know about the direction of E which we have already learned. Positive charges வந்து E will be acting outwards, negative charge க்கு E will be acting inwards. So இந்த இடத்துல வந்து இந்த long wire ல வந்து we have positive charges stored in it. இந்த positive charges ல இருந்து field வந்து எப்படி act பண்ணா it will act outward like this. Supposing in this diagram it is only a one dimensional view. If you consider this as the cylindrical wire, then this as the infinitely long wire which has positive charge stored in it, it will have electric field emanating in all directions. So எல்லா directions ல இருந்தும் electric field will be emanating radially outwards perpendicular to the length. So E acts perpendicular to the length L and radially outwards. This you have to imagine, then only you can understand the symmetry. So now you consider the point P which is at a distance r from the wire. Now what will be the electric field here? Electric field inga kandupidikiradhukku இந்த ரெண்டு ends ல இருந்தும் we will take two charge elements, linear elements A1 and A2 which are symmetrically on both sides, present symmetrically on both sides. Join this A1 and P and this A2 and P. Direction of electric field எப்படி act பண்ணும்? Along the line joining A2 and P. So at P, field due to A2 will be acting along A2P, that is in this direction, and at P, field due to A1 will be acting along A1P, that is in this direction. So the resultant will act in this direction which is vector E. So the resultant will act in the direction of R. So it acts radially outwards. Not only for this point, if you consider symmetrically a point Q on the other side at the same distance R, then due to A1 field at Q will be you have to join A1 and Q, electric field E will be acting in this direction, and A to P, electric field will be acting along A to Q, and the resultant E will be acting here along R. So, you can consider, if you consider a circle like this, at all points which are at the same distance from this point, you are considering a circle, like you are considering a circle with this R as radius, you are considering a circle. At all points in this circle, the electric field will be the same E. So, we conclude this cylindrical, infinitely long charged wire is having a cylindrical symmetry. So, the Gaussian surface which we have to imagine is a cylindrical surface. So, now we will pass on to the next one. Okay, now the Gaussian surface is a cylindrical surface. So, let me draw the long wire of length L which has positive charges stored in it, and the Gaussian surface is a cylindrical surface which can be drawn around this wire like this. So, this is the Gaussian surface, this is the Gaussian surface, and now the whole Gaussian surface can be divided into three parts. For derivation purpose we are doing this. So, this is the cylinder, this is having three different surfaces. One is the curved surface which is the center part, and the top surface and the bottom surface. So, I have mentioned this in the diagram. So, this is the curved surface and this is the top surface and this is the bottom surface. So, electric field, you have to remember, electric field will always be acting away, outwards, like this, radially outwards in all directions, that you have to remember. So, we want to find the electric field. For this, let us take this equation. Phi E is equal to closed integral E vector dot dA vector is equal to Q enclosed by epsilon naught. Now, this closed integral, this Gaussian surface, we are dividing it into three parts. One is the curved surface, the top surface and the bottom surface. So, splitting this expression into three different parts. One is integral for curved surface E vector dot dA vector, A vector dot B vector is equal to AB cos theta, that we know. The same thing we are applying here. E vector dot dA vector is EDA cos theta, plus another one surface is top surface. So, integral top surface EDA cos theta plus integral bottom surface EDA cos theta. So, in all these three cases, that is for all the three surfaces, we want to find theta, which is the angle between E and dA. So, first let us find for curved surface. Curved surface, in order to find E, let us consider a very small area element dA. This is a very small area in the curved surface. So, the direction of area will be acting, how it will be acting? Outwards, radially outwards. Direction of the area is drawn perpendicular to the area. So, dA, direction of dA, the area element will be acting outwards. dA vector will be acting in this direction, and already we know E will be acting, E will also be acting radially outwards. So, E and dA both act in the same direction in the curved surface. So, theta is 0 for curved surface. Now, take the top surface, take a very small element in the top surface. For this very small elemental area dA, direction of dA, see this is the top surface, direction of dA will be acting perpendicular to the surface. So, dA will be acting upwards, but E, how it will be acting? Outwards, like this. So, here dA vector and E vector are perpendicular, that means theta is 90 degree. Now, coming to the bottom surface also the same case. See, bottom surface, in this bottom surface we are taking a very small element dA. Direction of dA will be acting perpendicular to it, like this, downwards, and E will be acting outwards like this. So, the angle between dA and E will be theta is equal to 90 degree. So, curved surface theta is 0. Top surface theta is 90 and bottom surface theta is 90. We all know cos 0 is 1 and cos 90 is 0. Substitute. So, phi E will become here theta is 0, cos 0 is 1. So, you will have integral curved surface. Curved surface I have written it as CS, integral CS, EDA, cos 0 is 1. So, we will have EDA, and all these two terms will become 0 because theta is 90, cos 90 is 0, here again cos 90 is 0. So, this term will become 0, this term will become 0. We are left out only with this curved surface. So, phi e is equal to integral curved surface EDA is equal to what? Q enclosed by epsilon naught. Now, how to do the calculation? Phi e is equal to E. Now, integral curved surface EDA. We know E is a constant. E is a constant over the whole curved surface. So, we can take this E out of this integral sign and we are left out with E integral CS dA is equal to Q enclosed by epsilon naught. What is this curved surface area? Integral dA is A, and A is nothing but the curved surface area of the cylinder. What is the formula for curved surface area of the cylinder? 2 pi r h. Here the height we have taken as the length L. So, instead of h we have to write L. So, integral curved surface area will be 2 pi r L. So, curved surface integral dA is equal to 2 pi r L. Now, substitute here, you need not write this phi e, we are going to equate this and find E. So, E into, for this we have to substitute 2 pi r L. So, E into 2 pi r L is equal to Q enclosed. What is this Q enclosed? Q enclosed is lambda into L. So, lambda into L by epsilon naught. Both sides L will get cancelled and you will have E is equal to lambda by 2 pi epsilon naught R. So, this is the magnitude of E. If you want to write it in the vector notation, how will you write? E vector is equal to 1 by 2 pi epsilon naught lambda by R, R cap. Because E vector acts radially outwards in the direction of R. So, unit vector is R cap. Now, children, finally we have derived the expression for E as E vector is equal to 1 by 2 pi epsilon naught lambda by R, R cap. So, now what are all the interpretations we are going to make in this? So, first thing we will see about the magnitude of E. Magnitude of E, we are going to compare the magnitude of E for infinitely long charged wire with the point charge. Point charge which we have already derived in the initial part of our lesson, E is equal to 1 by 4 pi epsilon naught Q by R square. So, in this case we find E as proportional to 1 by R square, but in this case for an infinitely long charged wire we got the expression as E is equal to 1 by 2 pi epsilon naught lambda by R, from which we understand E is proportional to 1 by R. Just comparing the electric field for point charge and infinitely long charged wire. Now, coming to the direction of E, we can very well understand from this equation. Already we have mentioned also E will be acting outwards, radially outwards. It is perpendicular to the length of the wire, radially outwards. That is why we have mentioned R cap here. And the one more thing we have to see is, we have derived this taking only positive charge, but sometimes there may be negative charge also. So, for positive charge, the lambda will be greater than 0. So, lambda is greater than 0 means E is going to be positive. E is positive, and also it will, for positive charge, E will act outwards. How will you mention it in the diagram? So, this is the infinitely long charged wire having positive charge in it. E will be acting outwards in the direction of R. So, it will act in the direction of R cap. Now, for negative charge, lambda will be less than 0. So, if lambda is less than 0, E will be acting inwards. Less than 0, negative charge, E will be acting inwards. How it is acting? In the direction opposite to R cap, that is minus R cap. It acts in the direction of minus R cap. Now, we have made our derivations only for infinitely long charged wire. And this expression what we have derived may not be true for a finite a wire of charged wire of finite length, because in the case of finite length, supposing if you are taking a finite wire of finite length, then we can't apply this formula, because we will get the electric field value only approximately. Why? What is the reason behind it? Because the electric field may not be uniform at the ends. Ends la vandu electric field may be diverged like this. So, even if you are considering a finite length wire, we cannot take the ends where the electric field is divergent. We should only consider the middle portion of the wire. So, this formula, this law can be applied only for electric field due to infinitely long charged wire. Okay children, now we will pass on to the second application, finding the electric field due to a charged plane sheet of infinite area. We are going to consider a plane sheet like this. This is a finite one, but you have to imagine an infinite area, plane sheet of infinite area like this. If you imagine the plane sheet like this, it is having charges stored in it. I have drawn the charges, positive charge stored in it in the plane sheet. So, we all know electric field will be emanating outwards from the positive charge. So, it will be, electric field will be emanating outwards both on the right hand side and the left hand side. So, again the same case, we have to find the, imagine a Gaussian surface. First we have to find the symmetry for that. So, let us consider a plane sheet. Plane sheet which has positive charge stored in it. Let us explain about the enclosed charge. Charge enclosed in the area, we are going to consider a small area in this. In this area, charge enclosed is Q enclosed. So, charge per unit area will be, which is nothing but surface charge density, sigma. Already we have seen this. Charge per unit area, which is surface charge density, sigma, is the total charge enclosed divided by area. So, sigma is equal to Q enclosed by area. So, Q enclosed will be sigma into A. This we will be substituting in our derivation. Now, from this area A, at a distance of r, let us consider a point P. In this point P, the electric field is emanating in all directions. It is uniform both on the right hand side and the left hand side. So, not only this point, if you consider any point above and below, the electric field will be the same. So, with this P as center, you consider an area A, the same area A. So, this electric field will be the same at both the point P and on P dash. P dash we are considering on the other side of the plane sheet. The plane sheet is like this. We are considering one point P at a distance r from the plane sheet in the right hand side. So, by symmetry we are considering another point P dash at the same distance r, this side, left hand side P dash. Here again we are considering the same area and the electric field will be the same at all points. So, with this as the two surfaces, let us draw the Gaussian cylinder like this. So, this Gaussian cylinder has three different surfaces. One is the curved surface. Here the cylinder is like this. Previous case, the cylinder was a vertical cylinder, vertical Gaussian cylinder. Here we are considering, since it is infinitely charged sheet, we are taking a particular area. We are considering only a horizontal Gaussian cylinder like this. So, again in the previous, as in the previous case, it has three different surfaces. One is the curved surface, another one is the surface P surface, and then P dash surface. So, we have three different surfaces. So, taking this into considerations, let us pass on to the derivation. Before passing on to the derivation, how to find the angle theta. Previous case, how we found the angle between E and the area vector dA. The same way, for all the three surfaces, we have to consider small area elements dA. First, let us take the curved surface. Curved surface, consider a very small area element dA. The curved surface is like this and the area element you are considering like this, and the direction of area element must be drawn perpendicular to the area. So, the direction of dA will be perpendicular like this. E, as you all know, E will always be acting, this is the plane sheet, E will always be acting outwards like this, E will be acting like this. So, in this case, the angle between the E vector and dA vector is theta is equal to 90 degree. In the previous case, we got for curved surface as theta 0, but in this case, we are getting theta is equal to 90 degree. You should compare and learn, children, then only you won't make any mistakes. Now, consider this like how we had top surface and bottom surface in the previous one. Here we have two surfaces, one on the right hand side and one on the left hand side. This surface P and this surface P dash. Now, take the surface P, you consider very small area element dA. So, like this. So, the direction of area element will be perpendicular to the area like this, and E is also acting outwards. So, angle between E and dA is 0, theta is 0. Considering this surface also, here again electric field will be emanating like this. This is the plane sheet, electric field will be emanating both on the right hand side and left hand side. So, here again for this area P dash, you consider very small area element dA, direction of dA will be perpendicular like this, and E also acting in the same direction. So, angle between E and dA is theta is 0. So, for the three different surface, curved surface theta is 90 and the surface P and P dash theta is equal to 0. Okay, now we will do the derivation. We all know that already the expression we know, phi E is equal to closed integral E vector dot dA vector is equal to Q enclosed by epsilon naught. So, this expression we are going to split into three parts. One is for the curved surface, another one is for the surface P, and another one is for the surface P dash. So, curved surface, integral curved surface E vector dot dA vector is EDA cos theta. So, integral curved surface EDA cos theta plus integral P area EDA cos theta, integral P dash EDA cos theta. And for all these cases we have already seen what is theta. Curved surface it is 90 degree, and for area P theta is equal to 0, for P dash theta is equal to 0. So, theta 0 means cos 0 is 1. So, we will have these two terms we will have, but cos 90 is 0. So, this term will become 0. So, finally, we will have only these two terms, cos 0 is 1. So, we will have integral P EDA, integral P EDA plus integral P dash EDA is equal to Q enclosed by epsilon naught. So, this E is uniform throughout. So, P and P dash both are lying at the equidistant from the infinite sheet on both sides. So, we can take this P and P dash as P itself, and E is also uniform, take it outside the integral sign. So, you can just add the same value only, you can just add 2E, area is also the same, integral P dA is equal to Q enclosed by epsilon naught. Integral dA is A. So, 2E into A is equal to Q enclosed is already we wrote sigma into A by epsilon naught. Both sides A will get cancelled. You will have 2E is equal to sigma by epsilon naught. So, E is equal to sigma by epsilon naught. This 2 will, if you take this 2 to the next side, it will go to the denominator. E is equal to sigma by 2 epsilon naught, which is the magnitude. If you are writing it in the vector notation, E vector is equal to sigma by 2 epsilon naught n cap. This, what is this n cap? It is the direction, it mentions the direction of E which is acting outwards. E is a n cap is the unit vector normal to the plane. This is the plane, n cap is unit vector normal to the plane acting outwards. So, we have derived the expression for the electric field due to an infinite area, plane sheet of infinite, charged plane sheet of infinite area. Okay, now we will do the final discussion, children, of the equation what we derived now. E vector is equal to sigma by 2 epsilon naught n cap. We can see this electric field due to an charged infinite plane sheet does not depend on R, like what we had previous expression E is equal to 1 by 2 pi epsilon naught lambda by R. In that expression, or also for point charge, E was the magnitude of E depends on R, but here in this case the magnitude of E does not depend on R, it only depends on sigma, which is the surface charge density, does not depend on R. This is the point which we have to remember clearly. And the same thing what we discussed previously, for a positive charge, the surface charge density sigma will be greater than 0, positive charge E will be acting outwards in the direction of the unit vector. But for negative charge, surface charge density sigma will be less than 0, E will act inwards, that is in the direction opposite to the direction of unit vector. Now, the same case what we discussed in the previous case, this equation is true only for infinite charged plane sheet. It cannot be applied for a finite area, the plane sheet of finite area, because in the case of a finite area, electric field at the mid region it will be acting outwards like this, but at the ends if you see the electric field will not be uniform, it will be divergent. So, even if it is a finite plane sheet, we can apply this equation only for the middle region. It cannot be applied to the ends. So, this is true only for an infinitely charged plane sheet. Children, now we will pass on to the third application. which is the electric field due to two parallel charged infinite sheets. Actually in this we are not going to derive anything because already we have derived the expression for electric field due to an infinitely charged plane sheet, which is E is equal to sigma by 2 epsilon naught. The simple case here is that we are considering two plane sheets which are placed parallel like this. One plane sheet is having positive charge stored in it, another plane sheet having negative charge stored in it. Both are having the same surface charge density. This is having surface charge density plus sigma and this plate is having surface charge density minus sigma. Now we are going to find the electric field at three different points. One P1 which is present in between the two plane sheets. These are the two plane sheets and the point P1 we are taking in between the two plane sheets. And P2 and P3 we are taking outside the plane sheet, one on either side. So P2 we are taking this side and P3 we are taking this side. We will find out separately for these 3 points. What we have studied previously we are going to apply here. Like we discussed in the previous case, the electric field due to positive charge, sigma is greater than 0 now, it will act outwards. Positive it will act outwards, negative it will act inwards. This we have to keep in mind, then only we can draw the direction of the electric field. Electric field will be uniform at all places inside in between the two sheets. Electric field will be emanating in parallel directions outwards from the plates. So here at this point P1, the electric field due to the positive charge will be acting outwards like this. This is E plus, the direction of E plus. And now electric field due to the negatively charged plate will be acting inwards. Negative charge nokki irukum. So it will act inwards like this, E minus. So in this case, if you just see, the direction of E plus and E minus are in the same direction. Both E plus and E minus act in the same direction. So the net electric field will add up. Now come to this point P2. Here for this point P2, electric field E plus due to positive charge. Positive charge now outwards. So E plus will be acting outwards like this. Negative charge towards the negative charge like this, inwards. E minus will act inwards. So compare this one and this one. Here E plus and E minus both act in the same direction and the net electric field adds up. But here the electric field due to positive charge it acts outwards and negative charge it acts in the opposite direction inwards. So they both, because the electric field is uniform at all points, both will get cancelled. Equal in magnitude but opposite in direction, so both will get cancelled. Now consider this point. For this positive charge it will act outwards like this, E plus, and negative charge it will act towards like this, E minus. So here again positive charge act outwards, negative charge act inwards. So both are equal in magnitude but opposite in direction, so they both get cancelled. So the net electric field outside the two plane sheets is 0. So at any point outside the two plane sheets electric field will be 0, but electric field at any point inside, in between the two plane sheets, we have to add the net value. Like we have already derived the expression. So for both E plus and E minus we can say take the same thing. So any point inside the in between the two plane sheets, E inside is equal to E plus plus E minus. And E plus E minus both are same, equal in magnitude. You can substitute the same thing, sigma by 2 epsilon naught plus sigma by 2 epsilon naught, half plus half is 1. So if you add 2 sigma by 2 epsilon naught, 2 will get cancelled. So net electric field in between the two plane sheets, E inside is equal to sigma by epsilon naught. So this is a discussion which is made with what we derived in our previous section. Now the Now we will come to the fourth application of Gauss law, which is the electric field due to a uniformly charged spherical sphere. This is a spherical sphere. Whatever charge we stored in a spherical sphere, it will get itself uniformly distributed on the surface. Charge is uniformly distributed on the surface of the sphere. So it's very simple. It is having a spherical symmetry. So the Gaussian surface is a spherical Gaussian surface. So here we are considering a spherical sphere which has positive charge stored, it will get it itself will get stored uniformly distributed on the surface. We are considering a spherical sphere of radius capital R. Electric field, positive charge means electric field will act outwards. So at all points on the sphere, electric field emanates in all directions, that is electric field acts radially outwards. This is the direction of electric field. Now in this case, the total charge that we have stored here in this sphere surface, the total charge present on the surface of the sphere is Q. So this we have to remember, and the radius of the sphere is capital R. Now we are going to see three different cases. The first case is the same way like what we did previously. Here again we are going to see three cases. One is finding the electric field at any point outside the sphere. So outside the sphere, if the point P is present outside the sphere, what will be the electric field? If the point P is present on the sphere, what will be the electric field? If the point P is present inside the sphere, what will be the electric field? So first we will consider the first case. The point P is present outside the sphere. See, this is the sphere which we are having positive charge stored uniformly on the surface. It is having a spherical symmetry. So we are going to consider a point P at a distance small r from the center of the sphere. The radius of the sphere is capital R. So with this point P and with this small r as radius, you can imagine a Gaussian sphere. Since it is having a spherical symmetry, at all points on the Gaussian sphere, the electric field will be uniform E. It will be E vector. So now the charge enclosed inside this Gaussian sphere. What is the charge enclosed? The total charge, what we told, total charge is Q. So charge enclosed by the Gaussian sphere, Q enclosed is just Q. That alone you remember. Now the derivation, for the derivation we will use the same equation. Phi E is equal to closed integral E vector dot dA vector is equal to Q enclosed by epsilon naught. Here the closed surface, what is the closed surface? The Gaussian surface which we are considering. The Gaussian surface is the spherical surface. Gaussian sphere. It is a Gaussian sphere. E into E vector dot dA vector is EdA cos theta is equal to Q enclosed is Q by epsilon naught. Now on this sphere, Gaussian sphere, let us consider a very small charge element of area dA. Direction of dA, this is a sphere and here we are considering an area. Direction of the area will be perpendicular to the area like this. dA will act outwards. That will also act radially outwards. Direction of E is also radially outwards. So both E vector and dA vector act in the same direction radially outwards. Therefore theta is equal to 0. So theta is 0 அப்படின்றதுனால cos 0 வந்து என்னது 1. So Gaussian closed integral Gaussian sphere E into Gaussian sphere I have written as GS E into dA because cos 0 is 1. E into dA is equal to Q by epsilon naught. Now what is the we have got the expression Gaussian sphere, closed integral Gaussian sphere, E into dA. E is uniform, so you can take it out of integral sign. So we will have integral dA. Integral dA is A, which is the total area of the Gaussian sphere. Because it is a closed integral, it is the full area of the Gaussian sphere, which is the area of the sphere. Area of the sphere is 4 pi r square. So this will be equal to 4 pi r square. So in this equation, E you write it as such, closed integral Gaussian sphere dA, this is value of this is 4 pi r square, which is equal to Q by epsilon naught. So this 4 pi r square, take it to the other side, multiplication, it will go to the denominator. So E is equal to 1 by 4 pi epsilon naught Q by r square. So this we can write in the vector notation as E vector is equal to 1 by 4 pi epsilon naught Q by r square r cap. So here direction of E is radially outward r cap. So similar to point charge, this is the expression what we wrote for point charge, the electric field due to a point charge. So the charge that is distributed in a sphere will behave as a point charge. It will behave as if the whole charge is concentrated at the center. That's why we have got the expression similar to that of the electric field due to a point charge. In case A, we took the point P outside the sphere and we derived the expression E is equal to 1 by 4 pi epsilon naught Q by r square, which is similar to that of the electric field due to a point charge. So now we will go to case B. When the point P is on the sphere, So if the point P is present on the sphere, the radius of the sphere and the distance of the point both will be this. That is, small r will be equal to capital R. So in the expression what we derived, we have to substitute, instead of small r, we have to substitute capital R square. So that's all children, nothing more than that. Now the case C, in which the point P is inside the sphere. Now I have drawn the sphere. This is the sphere in which the positive charge is stored. Now I am considering the point P inside the sphere, and the distance of the point P from the center is small r. The radius of the sphere is capital R. The radius of the Gaussian sphere is small r. Here you can compare small r and capital R. Small r is less than capital R because P is present, situated inside the sphere. So the Gaussian sphere. So what is the charge enclosed by the Gaussian sphere? Inside the Gaussian sphere we don't have any charge. The charge is present only on the surface of the sphere. Inside the Gaussian sphere there is no charge. Therefore charge enclosed by the Gaussian sphere is 0. That means Q is 0. So in the expression what we have, E vector is equal to 1 by 4 pi epsilon naught Q by R square R cap. This Q is 0. If Q becomes 0, E will also become 0. So what is the conclusion? The electric field inside the sphere is 0. Inside the charged sphere is 0. So we will just conclude with a small graph in which on the x-axis we have taken the distance r of the point P from the center of the sphere, and the y-axis we are taking the value of the electric field. Now the radius small r and capital R is equal in this point. This is 0 as r increases, and this point r reaches a value equal to capital R. So here in this side r is less than capital R. In this side r is greater than capital R. So this is the portion in which the point P is present inside the sphere, and this is the point in which the point P is present on the sphere. And these are the portions in which the point P is present outside the sphere. Like we discussed 3 cases, we considered a sphere, charged sphere. If the point P is situated outside the sphere means R is greater than R, outside the sphere, this portion of the graph. And this point, small r becomes equal to capital R. This is the case in which the point P is situated on the sphere. And these portions, the left hand side, small r is less than capital R, which means the point P is present inside the sphere. So inside the sphere the field is 0. So there is no field. The field is 0. As we move in this direction, the field is only 0. When we reach this point small r, when small r is equal to capital R, that is when the point P reaches the surface of the sphere, electric field is maximum. That's why the electric field is here. But as r increases, as point P moves outside the sphere, electric field decreases, because we can very well understand from the equation E decreases as r increases, because E is proportional to 1 by r square. So as r increases, E decreases. Less than r means E is 0, because we don't have any charge enclosed inside the sphere. Equal to r means E is maximum, and greater than r means E, as r increases, E decreases. So with this we conclude this session, children. So today we have seen 4 different applications of electric field. Infinite long wire, charged infinite long wire, and then charged infinite plane sheet, and then parallel sheets, charged parallel sheets, and then finally charged sphere. All these 4 applications are equally important. Gauss law itself is very, very important. You can expect any 2 applications, 1 or 2 applications in your public examinations. Thank you, children.